Okay, so my name is Caleb Jones, and I'm a software engineer at the Enterprise Data Solutions Group inside Disney. And one opportunity there is the opportunity to work with lots of different kinds of databases. And one of which I've been able to do some proof of concept work on is graph databases. So this talk, not knowing what the whole spectrum of people's exposure to graphs are here, I wanted to cast kind of a wider net. And so there's probably about 4 sections to this. There's kind of an intro, why graphs, what are some of the opportunities there, what is a graph, very rudimentary, and I'll fly through these. So don't think that, oh gosh, it's going too fast, I'm not going to be able to catch up. And then we'll talk about the specific technologies, and those are Tinkerpop, which is graph framework, Titan, and then also specifically we'll do a lab around Gremlin. It's a query language. All right, so why graphs? I like to talk a little bit about history first. So this guy is really cool, Warren Weaver. He was a scientist in the first half of the 20th century, and he wrote this essay titled Science and Complexity back in 1948. And he tried to categorize science into kind of 3 epochs here. One he said was kind of pre-19th century, which he titled Problems of Simplicity. And that basically is kind of Newtonian mechanics, one element interacting with another element. And as you know, as soon as you start adding more and more elements in that system, Newtonian mechanics kind of breaks down and it becomes very unwieldy. So he saw that, being a scientist the first half of the 20th century, and he saw what was happening with a lot of the newer modeling that was going on, and he kind of titled that a problem of disorganized complexity, where now the mathematics and the physics is dealing with systems, understanding systems. But it's doing that not from the element interaction up, it's doing it from the outside in, kind of more statistical modeling. And then he stopped there and said, okay, well, what opportunities or what breakthroughs could happen next? And he's trying to pontificate a little bit, and he labeled this the problem of organized complexity in this essay. And he basically was saying, again, this is 1948, so then I grabbed a picture of it yesterday. This is the one of the fastest, I think it was the fastest computer right about the time he wrote this essay, the ENIAC, if I'm pronouncing that correctly, could do about 5,000 operations a second, somewhere around there. It had little to no RAM. But anyways, he saw that if computational power ever exploded, that it would open up this opportunity to begin understanding systems in terms of the interactions of the elements in the system, and not just at the system kind of black box level. And he really, what he's describing there is graphs and graph theory, and now what we're starting to be able to do with graph databases and how we model things. So anyways, a little bit of history there, which I find interesting, kind of sets up the underpinning of this has been a long time coming, as with a lot of technology. So I wanted to go through a few different examples contrasting trees and graphs. And my purpose here isn't to show, look, trees are bad, graphs are better. Trees are important, we need to use them for modeling certain things, but there are different tools for different problems, and it's important to understand the differences and what they can do. So on the left here we have, I think this is from Darwin's Origin of Species, this is a species tree, and on the right we have a kind of overlaid on top of that a bacteria, common bacteria across different organisms. Knowledge comes up in knowledge classification. On the left we have this taxonomy. I think it was, I'm going to butcher the name, but French philosopher Diderot, if I pronounce that correctly, but he did this in the 18th century. And then now what we have is Wikipedia, and on the right there is a network of links between articles and categories in Wikipedia. Right, it starts to look almost organic. We're all probably familiar with this, right? And anyone who's worked professionally in academics, and I don't want to knock that. I mean, you need hierarchies for certain problems, but again, right tool for the right job. But anyone who's worked in even a small company or to even a larger company knows that what really goes on day to day in terms of interactions looks much more like this, right? Right? There's the hierarchy isn't quite as represented there. Another one, neurology. On the left, you have that kind of phrenology, this notion of particular section of the brain is responsible, or the area of the brain is responsible for one particular thing, And more as we're understanding neurology and doing models that, like, I think this was the Blueprint project, and it tried to map a certain portion of the neocortex. It's a graph, right? There's these connections there, and it shows that really there's no one section that's responsible solely for one particular thing. It's really a network, an interaction of many different systems. It becomes very complex. So that's a few contrasts. Some things to think about, right? Trees might be good for linear, categorical, symmetrical, kind of convergent modeling, whereas networks allow you to do different things. Multi-dimensional, you can have different edges with different types, and it allows for more divergent modeling. And so right tool for the right job. We'll go even faster through these. This is a web of species interactions in a climate. Here's NSFNet. This is a slice of the internet in 2005. Any guesses on what this is? This is the political blogosphere. So you can see the polarization right there. This is Steam social network. This one's really interesting. This is a circle graph of protein interactions or different chemical interactions in a cell. And I know, even for someone like me who knows very, very little about biology, I find it interesting. I know just enough to know that ADP and ATP are prominent chemicals in the operation of the cell. And sure enough, you can see those at about 1230 towards the top there. Those hubs are ADP and ATP. Anyone's familiar with Neo4j? There's a offshoot technology from that called Bio4j. So anyone's interested in biology, go check that out. It's really interesting what they're doing. I had to put a little Disney reference here, right? So here's character interactions in Toy Story. Here's one that I did. It's more of a kind of a spoke tree, but still a graph. This is a visualization of a Git repository that I worked on. Here's another visualization I did. This is Marvel comic book character interactions for a comic book series. On the left there, I think, is Uncanny X-Men. On the right is Avengers. So anyone's interested, I think it was mentioned, John mentioned it, what is it, Gephi is the tool I use to do this visualization. Very good tool for once you have your graph all loaded up, imported into Gephi, you can do really interesting visualizations. Anyways, so that's kind of a whirlwind tour of some of the different things that are being done with graphs, where they've come from. Here's another one. This kind of gets almost metaphysical, right? You see these common structures at the microscopic and macroscopic level. And I put this here mainly because I started with Warren Weaver, right? He was saying, hey, once technology starts to really boom in terms of compute power, we'll be able to start doing these things. And a prime example of that is the Millennium simulation that they did in 2005. That was, I think I have it, 25 terabytes of data. I'm modeling 20 million galaxies. So that's the sort of thing that I think Warren Weaver was right on when he was pointing that out. And graphs are very much at the center of this. Companies are using it. There's recommendation engines. Google's PageRank, those that are familiar with that algorithm at all, it came from an algorithm called the eigenvector centrality algorithm, I believe. It's kind of a modification of that. But it came out of graph theory. Pathfinding, right? Who's here been on LinkedIn, right? It's always recommending you. This person knows this person who knows this person. You might want to connect with them, right? That's graphs. And then Facebook, probably heard about graph search. Does anyone know? I thought I heard that it was Neo4j that was part of that project. I don't know. So it's coming up more and more. And again, it's when the right how to put it, the right tool for when you have the problem of you're more interested in the interactions with your elements in the system than you are with just understanding them in isolation. When that starts to occur, that's really when you need to start thinking about graphs and graph databases. All right, so for those who may be thinking, okay, I still don't know quite what a graph is made up of, here I put just a few slides in. So that was kind of top level down. We're going to go bottom up and then get to the technologies. So graphs, it's pretty simple. At the very base of it, you have nodes or vertices that can have edges coming into or out of them. Okay, and they don't have to have edges. You can have nodes. You can have a graph that's full of nodes that aren't connected to each other. That's perfectly fine. Not terribly useful, but you can do that. And then an edge, right, just goes between two nodes. But conversely, an edge, you're generally not going to model an edge in space pointing to nothing, right? And indeed, as we'll see, I think, yeah, in one of the slides, I talk about how in Titan, if you go and delete a node that an edge points to, it deletes that edge for you. So don't worry about this, but just know that, and this comes into play when you're doing something like modeling, like how Titan models things in Cassandra, but often the connections in a graph can be modeled as an adjacency matrix. And there's a whole branch of mathematics there that you can do really interesting things to understand things. But just know that that's often a tool that's used by graph databases to model connections. And you can have different types of connections, right? There's a little bit more complex graph. But this is the slide I want to get to, property graphs. A lot of the graph databases, this is how it's modeled. So you have those nodes and you have those edges, and you just are assigning key value pairs properties to them. Oftentimes, I know Neo4j, Titan, it's what you might call schema free, right? There you can create a node and it doesn't have to have a certain set of attributes or anything. You just create a node and start tagging it basically. And another important thing here is that one way it's different from relational databases. You could look at this and think, well, I can model this in a relational database just fine, and you can. And there might be instances where you might want to. But one thing that sets graph databases apart is that they treat edges as first-class citizens. And we'll see this in the lab, that a lot of queries start at edges and then work their way out from there. And so that's an important thing to know when you're modeling, because there's a tendency to want to push all these properties into the nodes, because the nodes, you inherently think they're more important because they're nodes. You have to get away from that thinking and start thinking about where to put the right properties, and how you're querying and what you're querying for has a lot to do with that. An important part of graphs is traversals. Your typical computer science traversals, breadth first, depth first. And then a lot of query languages allow you to mix and match those. And then as you're traversing, you can do filters. You can be aggregating things as you're walking the graph. And then backtracking, which in a very imprecise way to put it, for me, an intuitive way to understand it is backtracking is like as you're traversing, you're leaving little breadcrumbs for yourself to go pick up after you're done. So an example might be, I want to find out, I have a genealogy graph, and I want to find out who Bill Cosby's grandfather is, but I'm starting at the top here, right? You'd be walking down, and then you'd eventually be filtering until you find Bill Cosby, but you don't want Bill Cosby, you want 2 levels up, right? So you leave these little breadcrumbs, these backtrackings for yourself, so that way when you do find them, you can get back up.
In the previous slide, where's the connection into stored? Is it stored in the edge?
In terms of the directionality of the?
Yeah.
Yeah, that's going to be stored as part of the edge.
It doesn't show in the attributes.
Yeah, it's kind of implied in the drawing. That's a good point, that at a certain point, the graph database has to store some flag, or usually what they store, you'll see a from and to, or source and target in there. And so you'll see actual IDs of nodes to give an indication of where it's coming from, where it's going. But that reminds me, notice at the bottom there that there is no directionality. And that's perfectly fine in modeling graphs. You don't have to have a source or a target. You can just have an arbitrary connection, like nose might be one, although that might be directional. I might know someone, they might not know me. But what would be a better example? Brother, right? Brother. If I'm brother of someone, guess what? They're a brother of me, right? So directionality plays a role in the modeling, but there can be instances where you don't have directionality. All right, so that's a kind of low-level view of graphs. So hopefully, if anyone here came here thinking, "Oh gosh, I have no idea what graphs are," now you hopefully have a clearer picture. And those who already did it, then a little refresher course doesn't hurt. All right, so Tinkerpop. So let's get to some technology here. So who here has heard of Tinkerpop? Just show of hands. So we have maybe about half, maybe a third. Okay. So Tinkerpop, and a lot of these are my own definitions, so, but it's in my opinion, it's a comprehensive open source graph framework. It's really their breadth of their vision with this is quite good. And I'll go into each one of these. They have these cute little characters they've come up with to represent each of them. It works. Iconography does a lot. So blueprints, think of it as JDBC but for graphs. Pipes, this kind of data flow chaining framework that they use under a lot of the covers. Gremlin, which we'll be spending a good portion of the time on here. Frames, think ORM, object relational mapping, but for graph databases. Those who might be familiar with JPA or Hibernate, it has a similar feel. Furnace is just a set of graph analysis algorithms. And then Rexter is their cute little dog they have here. But it takes all of those APIs and provides a set of RESTful APIs, or it also has a binary protocol for interacting remotely with all of this. So the stack comes together like this. So a lot of these components build on each other. Blueprints is at the bottom. You have frames and Gremlin, which will compile down into pipes and blueprint commands. And blueprints, just like any decent abstraction layer, is going to plug into lots of different systems. I know of 4, hopefully these aren't too out of date, but I know of 4, Neo4j, Sail, OrientDB, and Dex, which are official supported ones, but then they also have a whole host of third-party implemented connectors, and Titan being one of them. They also, I found this interesting, they have a MongoDB one. I have a fair amount of experience with MongoDB, and they have a whole page about how you can model graphs. And it's interesting because it'll work for certain use cases, but in my experience, when you want to go edit the graph, it becomes very, very difficult. And so that's interesting. They have MongoDB there. Someone took the time to do that. All right, so let's move on and zero in on each one of these. So Rexter, I mentioned it provides this REST API. It also has a very flexible extension model. So that's actually what was used to implement the Gremlin. So you can send Gremlin queries to Rexter and it will execute them. It has, those who might be familiar with Neo4j's web UI, they have one that's similar. I haven't done a full side-by-side feature comparison. Theirs is called Doghouse. And there's a command line tool. And then it also has a pluggable architecture, and people have done things like written security plugins and plugins that talk with different kind of backends. And there's the website there. Furnace, we talked about breadth first, depth first kind of search, but there's also, these might be familiar, those with a computer science background, things like A*, shortest path, Bellman-Ford, I mentioned PageRank before, and then degree distribution. Degree, basically when you have a node and you have connections coming into or out of it, the degree is essentially the count of those connections. And that becomes really important when you're starting to do graph analysis. You want to find those nodes that have high degree count. And it can be either in degree or out degree or just an absolute degree. And PageRank is one algorithm. It's not the same thing as degree distribution, but it takes into account the degree distribution somewhat and your relation to those high connectors. So there's another presentation I've given before on Gephi and some social network analysis. That's a lot of fun. It's one area where I enjoy working quite a bit. Tinkerpop. So rather than just do another bullet point here, I thought some code would be interesting. And this is an example pulled from their website. So again, those who might be familiar with annotation-based persistence frameworks, it's going to be fairly familiar. You can map properties to field values. You can map relations to lists in your object. And then you can also map queries to objects themselves.
I want to pull the other screen.
Sure.
As I can see from that.
And then loading them really is quite simple. The bottom there is a few lines of code. Once you have your graph object, you're just doing, they call it a vertex instead of a node. And even though I'm looking at it and it says vertex, my mind still thinks node. So you have to forgive me if I mix the nomenclature here. But it's really just say get vertex, give it an ID and the class you want, and it does all that mapping for you. Tinkerpop pipes. I don't have much experience working directly at this level. I just have a conceptual understanding, and I think that's okay because hopefully people are working at a higher kind of DSL Gremlin layer. But it's there. It's an API you can use, and it has these constructs like transformation, filtering, side effects, where once you find a node, you can make changes to it as you're going, deciding how you want to branch as you're traversing. And there's quite a lot. I think I counted. There's a little bit over or around 20 different types of filters that you can do as you're traversing. It's about 15 different kinds of side effects, and aggregations, grouping, counting, tables and trees. So there's a lot there. So if you're finding yourself in a situation where you have like a stream of of objects and you want to chain them through kind of a DSL, not a DSL, kind of almost like, it feels almost kind of like an ETL somewhat, but for graphs. This isn't an option that I've thought about before. Blueprints, it can work with lots of different backends. But another interesting thing I'll mention here is it can support transactions. It has transaction APIs, but of course that's only if your backend supports transactions. It's not going to necessarily go out of the way to implement it that if it doesn't, if it's not supported. And then format readers and writers. So there's common open frame formats for storing a graph. So if you have a graph of 10,000 nodes and edges, you can store it in a graph file format, and then move that around, and tools like Gephi can just pick that up and pull it in. And so they've written readers and writers for those. So that's really important. I use that as part of a proof of concept work I did where I was streaming things out of Hadoop into Titan, and then saved it out, and then loaded that up into to Gephi. So that's an important tool to have. All right, now Gremlin. And I'm going fairly quickly through these because I want to focus more on Gremlin here. So another show of hands, who's had some exposure to Gremlin before? Okay, just a few. Who's had exposure to, what is the Neo4j? Cypher. Okay, a few more. All right. So this is a little bit different. It has very similar constructs, but the way it's expressed is different. So it's written on top of the Groovy scripting language, and so it has much more of a procedural feel to it than Cypher does. There's trade-offs with that, but it has those same. This bottom section here should look pretty familiar too, right? That's a lot of the same mechanics that what was it? Not frames, but pipes. Yeah, thank you. So that pipes provided, and that's not a coincidence, right? Because Gremlin will leverage pipes as part of that stack. So here's a table I gathered. So hopefully people here are fairly familiar with SQL or SQL, however you want to pronounce that these days. And so I did some kind of analogous queries. So you might be doing some simple selects. You might be selecting certain fields. You might be doing some aggregation, right? You might be doing a distinct max, right? And these translate fairly nicely, fairly straightforward over into Gremlin. And don't worry if I'm skipping over this because we'll go through. I believe all of what's on this page.
Should we read the V operator here as logical or as vertices?
The V operator here, are you talking about like the
G.V?
Yeah, so the things you put, that's in there is a single operation to test if a property equals, and then I don't have it in here, but when you pass in two parameters, it's field name and then value for equality. And there's a 3-parameter one where you can do field name operator and then value. And then you can also do ors and ands and things like that. So it has the same constructs.
I think he's asking you, does G.B on say in the top row return a set of vertices that equal all users?
Yeah, so and it's interesting, there's a distinction between G dot capital V and G dot lowercase v with the Gremlin query language. G dot capital V says all the vertices, here's the criteria that I'm going to give you. G dot lowercase v is I want this particular vertice, and then start from there.
I don't think a wild stab out. Is there a G dot E?
Yes, there is, and a G dot lowercase e. So. Yeah. All right, so you can do there's that 3-parameter one, that second one down, and then you can do multiple criteria, so you can chain these things, right? So you're doing where the age is greater than 25 and the sex is male. You can do ordering, and this is where the line starts to blur between where does Gremlin end and Groovy start, right? Since it's built on top of Groovy, right, that looks an awful lot like you get some closure language going on in here in terms of this mapping and ordering that's in line there.
One question is, if you look at the sequel, you think about query optimizers. If this is a more direct map into Groovy, is there no room for a query optimizer?
Yeah, I don't know much about the query optimization that they're doing there. That's an interesting question, though. Yeah. Unfortunately, I haven't done a dive into that. Then this last one is kind of the hyperbole slide, right? So you can do joins, in my opinion, are much more natural in a graph type language, and I can say that with a fair amount of confidence. I have several years working just in a lot of different SQL systems, and you'll see this in a lot of presentations that Neo4j, that I've seen Neo4j do, is when you're doing, the more joins you're chaining in your query, the harder and harder and the worse and worse performance you get. And a lot of energy is spent in the relational databases trying to optimize those joins, either through denormalization or different techniques, and that's fine. I don't like to be on the pedestal of look how bad SQL is. Everyone needs to use graphs, right? Again, right tool for the right job, and there could be instances where you might want to model even a graph in SQL. But as you can see, at a certain point, it starts to break down in terms of performance and also in terms of just maintainability. That's an example query of a product recommendation, and on the right is an analogous query. So again, if you're finding that your key queries that you're trying to get at have more to do with the interactions, which are usually while you're doing joins, the interactions between different objects in your system, really start to think about graph databases. Right, and then we'll go more into Gremlin. Here I'll do another kind of example data modeling, but there's some resources. Tinkerpop has a lot of great documentation, and I'll send these slides out. I'll probably just post them up on SlideShare and put a link in the Meetup so that you can go grab those. So here's an example data set. This is the Tinkergraph data set, and I want to draw attention to, I posted in the Meetup, so if you're currently looking at a screen, you can go to the Meetup. I posted a bit.ly link there, and it's also, I wrote it up on the board over there. So not here, but later we'll be doing a data modeling of an example blog engine, and going through, and if people, hopefully you can go grab Titan if you haven't already. I think, John, you put that in the meeting notes or description. But while I'm going through this, if you haven't gotten Titan on your system, just go download it. I think we said version 0.32. I don't know if the new version won't work for what I've set up, but you can follow along here somewhat if you want. If you have Titan, just pop open the Gremlin shell and you can start playing with this. But they have in Gremlin, they have this under Titan, they have this Tinkergraph factory, and you have this create Tinkergraph, which is this dummy graph. And it's basically people and projects, and people know people, and people created projects. And so I wanted to go through and explain some of the basics behind Gremlin to kind of build up towards this lab that I'm trying to save as much time for. All right, so you can do vertice counts, right? You can do edge counts, just kind of walking down here. There's that lowercase v, g dot lowercase v, and I feed it the ID, the primary ID of the vertice, and it will go grab that particular one for me. But it doesn't return all the properties, it just returns essentially a reference to it. So if I want to go explode that and grab the properties, I got to do that .map command after it. And then you start getting into, under every vertice, there's this out E and in E. And those are essentially go grab all the edges that come out of me. Okay? And then go grab all the edges that are coming into me. And so you can grab all of them. So if you go to, right, who's Marco is number 1 there. And so if we go grab Marco and then say out E, we'll get those 2 nose edges that are going out, and then that one created edge that goes out. Then we can also filter by type. Well, I'm only concerned about who Marco knows, so you can go do out E knows. And then you can also grab the properties there. And in this graph, they're only using a property called weight. So you can do some more, like you can get all the vertices that are known by Marco, right? So we want to go grab these. We start at Marco, follow out the nose, and then this in V is the next one. And I get these mixed up, but what essentially this is doing is saying I want to go out of Marco, following the nose edges, and then I want to go into the vertices that those edges point to. And I get them backwards, but fortunately, this language is set up so it's very procedural kind of chaining, right? So if you ever get them backwards, you just take your query, lop it off halfway, and see what it's returning at that point. And then you can start building it back up again. You can do filtering. So you can say, well, I want to filter those people that Marco knows that are older than 30, right? And again, you can see that it's building up from that previous one. All it did is just added that filter at the end of it. Or you can get just the name. What was that? Yeah, so so this filter construct, so you see those are curly brackets there. That filter, you pass it essentially a closer function, and then that IT is the iterator as you're going through and doing that filter. And I'm not a groovy expert. I think I know just enough to be dangerous. Just enough to get by with using some of these things. So another interesting one is this notion is find nodes who know someone older than 30, right? So before, all these queries have been starting at Marco and then fanning out from there. So there we use a G.capital V because we're starting at all nodes, and I want to just find all the nodes who happen to know someone. So you can do that, and that's an instance where you need that backtrack, right? So notice we have that little X there, right? So we say I want start at V, and I want to leave a marker called X on all those guys, and then I want to filter out. I want to go out across the nose edge, and then I want to go into the next one. Then I want to verify that that edge that I went into has this criteria of being older than 30, and then once I've got to that point, I want to pop back and then give me all the X's that still are matching my criteria. So it's been, as you were traversing, it was filtering out those original nodes, those original vertices. You can get more fancy. Again, we were doing mainly vertice-based queries, so here we're doing edge-based queries, find all edges greater than this particular weight, find all the edges that came from Marco at this particular weight. Let's see, find the nodes that were created by other nodes, right? So we're starting to get into more answering questions that are a little bit more non-intuitive if you're doing kind of a join-based approach. That's another one we have there. Find all the nodes that were created by more than one node. Maybe it's because my SQL's a little bit rusty, but I kind of think, how would I model that, and then how would I go grab that? It starts to get a little bit unintuitive to me compared to doing this kind of an approach. Here's another one. This starts to feel a lot more kind of networky type question. Find the nodes, the bottom one there. Find the nodes created by Marco's friends, right? The people that Marco knows. And so there's that query there. I want to start at Marco. I want to go out to who he knows, and then I want to go into those people and then go out to any projects they've created, and then go into those projects, right? And so you can start getting kind of some intuition of how this traversal starts to work. You can add nodes, add edges, and there's some examples there. We'll see that in the lab, so I'm not going to spend much time there. And then you can query for edges. You can remove a vertex, remove an edge, and I show an example there of, hey, guess what? It's going to remove orphaned edges. So if you delete a node and there's an edge that was edges that were pointing to it, it'll clear those up for you. All right, any questions? I'm going to switch gears. We're going to talk about Titan for a couple minutes, and then go into get hopefully some hands-on work for a period of time. Yeah.
I'm just curious if you instead of working a command line, you're working inside Java, constructing an object. Are we dealing with the same set of syntax?
Yeah. So that's a good question. So the Gremlin query language is built on top of Groovy. So just like how you can be inside Java writing Java code and then send a Groovy, write Groovy and send that to the Groovy engine using, I think it's JSR 223 or 233. It uses that same mechanism. So there's ways that you can be in Java, write your Groovy query right there as a string, or build it up using a kind of a query builder, and then send it right over. Yeah. So you don't have to take this and then try to figure out how to compile it in yourself to pipes and all that. All right, so Titan. So hopefully people came here for Titan as well. I did some kind of proof of concept work with this. So Titan they kind of came onto the graph scene as kind of a different angle. They've been all about distributed backends, right? Where the line that they keep putting out there, and I've seen demonstrations where they're doing that, is that it can be optimized to work against millions, billions of nodes and edges, right? It's distributed, so you can build up your backend cluster to support what your needs are. They have theoretical limitations, they say, but I mean they're pretty ridiculous. So, although I will mention this, I saw an interview over at LinkedIn, and they use a lot of graph databases there, as I mentioned, and they actually ran into this, not particularly with Titan, but they ran into this problem where they couldn't load up their graph. And so what they have to do is pre-aggregations of, and I don't know exactly what the aggregation metrics are, but I'd imagine they might aggregate people with like interests, or people who are tightly connected hubs, and then that allows them to start modeling and doing some of the analysis they want. But if they just treat every single node as an individual person, they struggle trying to load everything up into a single machine. So Titan kind of comes with this promise of let these distributed solutions like HBase, Cassandra backends work with this. And they have some native integration with the Tinkerpop stack, which is why I talked about Tinkerpop. So if you're going to work with Titan, take a good look at the Tinkerpop stack. And they also support some more advanced indexing. So they don't do it in-house in themselves, inside the solution. Their approach is, if you need range querying, you need kind of more advanced index lookups, stand up a Lucene, or if you need that index itself to be distributed, stand up Elasticsearch. And then they you can configure that, so that way when you go to query and do that index, it'll branch out to Elasticsearch to get that. And it's all created by I think Aurelius, if I'm pronouncing that correctly. I think Aurelius is a Greek or Roman emperor, but anyway, yeah.
I'm sorry if this is a sort of a naive question, but I'm wondering if these graph databases at the bottom do they run, to what extent are they simply shells over the top of a relational database that emulate graph technology?
So
it sounds a little bit like that's what you're saying here. Cassandra is not a relational database. But
yeah.
Is that what are they using, like Cassandra as an engine behind?
Yeah, they're using Cassandra for the actual storage and the row and indexing. And so I might have pulled it out. Let me peek ahead here. No, I pulled it out. So because I didn't want to get into a big side discussion on Cassandra, because that's a whole other topic. But I mentioned before the slide mentioned adjacency matrices, right? And those you can actually model really efficiently in Cassandra, where you have row key, where you have a nodes key, and then the row keys can be the IDs of other nodes, and then
Right.
it indicates that it's, you know, just what the directionality is. And so doing that, you can start to do these traversals by traversing that kind of.
So, for instance, does like Neo4j do that, or do they have?
I don't know. I don't know what under the hood what Neo4j is doing. So when I was doing some of this proof of concept work, I had it going against Titan, and I took a peek at how it was structuring the column families and whatnot. So if you're interested, come up to me afterwards, and I can show you that slide that I ripped out of here. Yeah.
Am I wrong, or do you run into problems if you get nodes with a huge number of edges? Like, I got a node that connects to all of the other nodes in the system. Don't you start getting?
Yeah, so that's an interesting question. I don't know how they solve that. Where if you have a real hot node, essentially, where everything is connected to this person. Anyone who's kind of studied up on what is the 80-20 rule, right? That oftentimes 20% of the nodes contain 80% of the connections, and so you'll get certain hot spotting. So I'd like to think that they've mitigated that, but I don't know for sure. That's an interesting point. So the architecture, there's a few ways that you can plug this in, and they kind of categorize this as native, remote, and embedded. Where native, it's going to connect remotely to the cluster, so it's not going to be essentially it's going to be running right alongside your application, and then it's just going to have a connection pointing to Cassandra, right? Some of the limitation there is you could be bottlenecked by your application server since it's running right alongside of it, but it has that kind of a deployability. Another option is you can set up a different tier of machines that are essentially kind of processing machines that then connect to it. So it allows you to scale out that processing need separate from your applications. And then another option is embedded. And this, I haven't had experience deploying this way, but in this setup, you essentially place Titan and or Rexter on each one of your nodes in your, for instance, Cassandra cluster. And they even have an option where you could run it in the exact same JVM as the Cassandra process to eke out some additional performance. So the idea there is, just like how in Cassandra you just connect to a certain set of nodes there, and then the the gossip protocol and so forth in Cassandra handles the communication there. They can piggyback on top of that. But I'll mention, Cassandra's not a fool. It's not a silver bullet either. It has its warts, just like any other system. So be careful what you marry yourself to. Indexing. So they have a standard index that's internally handled to Titan, so you can index fields. But the limitation there is it's very fast, but it's only going to support exact matches. So you're not going to be able to do where it's less than 1,000 or between some date range. You're not going to be able to do that. And those who are familiar with Cassandra knows that's a pretty fundamental limitation with Cassandra itself. Doing range queries, you can do byte ordered partitioning, but it's kind of a faux pas. So you get hot spotted nodes real fast that way. You can do an external index. I mentioned that before. You can plug into an external system that will then give you those range queries, but they don't support it internally. And then there's a couple options there, Lucene and Elasticsearch. So limitations and gotchas, and I ran into some of these. So their limitations are present. In particular, this inability to create indexes or drop indexes on the fly. That kind of caught me by surprise as I was working with this. It's not that they couldn't do it, but I think there's a hesitation on their part, I think rightly so, to avoid this kind of arbitrary triggering of column family scans, which is really horrible for HBase and Cassandra. So I don't know, I could see them possibly doing that, but it's a surefire way to allow people to shoot themselves in the foot. So let's see what else. I mentioned that it'll delete. Sometimes you'll run into the situations where they'll get ghost vertices. I read about this in some of their bug system or their Google group, and they said it'll happen. and just have a process that can clean them up. So I didn't run into these, but know that that's a ghost that's out there. All right, so let's get to the lab here pretty soon, but I wanted to show this real quick as kind of what this looks like. You have Titan, and your application will send a Gremlin query to it. It'll split it across and run. If you have this distributed backend, it can run in parallel and then come right back out to your application. So that's the kind of the overall model there. All right, so I don't want to go too far past 8. I think we'll have just enough time to go through this data modeling example. So if anyone here has Titan on their machine, I'm just curious how many people are going to try to be following along, so I know not to blast past people. Okay. All right, so a colleague and I came up with this idea as we were exploring different database technologies of what's something beyond just hello world that exercises a few data modeling muscles, and then we did that. We sat down and did that in Cassandra, MongoDB, and then also Titan. So we came up with it's a few set of several basic requirements that you might see for a blog or a discussion board. And so we listed those here, and so this data modeling exercise is essentially going to be modeling in Titan, and we're going to be answering these queries. All right. So the first one, and I mentioned Cassandra there. I used to have instructions on how to run this and then connect it to Cassandra, but that's going to be too much to do here tonight. So those who have Cassandra, you can go ahead and fire up the Gremlin shell. I will come over here. Let's see if I can. Let's mirror displays so I don't kill my neck here. Okay, where am I? Okay.
Can you up the font size of that a little bit?
Yeah, thanks for the reminder. All right, so there's a little ASCII art that they pass back to you. Oh, I need to get out of presentation mode. Sorry about that. Let's just tab back and forth. And let me guess, that killed my mirror displays. Yes, it did. Okay, I think this will work. All right, so let's drag this. I don't need notes. All right, so we can fire up Titan here, the Gremlin shell. We're just going to be doing in-memory stuff. So modeling entities. I'll skip over this except to mention this one here. Don't shy away from putting things in edges. I already mentioned that before, but for me, at least I found as I started modeling things in graphs, I had to break this habit of let's push things into the nodes. I need to do that, and I don't know why I felt I needed to do that, but I found as I relaxed that tendency and started looking at edges as first-class citizens of where I'm going to start in key parts of my query, that helped me model things better. A general rule of thumb might be that you're going to model actors or elements in a system as nodes or vertices, and model the interactions between them as edges. That's a common thing. You could, I guess, model it differently, but you'll commonly see that in a lot of graph modeling. All right, so let's see if I can scroll, and that barely fits. So this is the overall network I came up with here. So we have these main elements in the system, these nodes, all right, users, posts, and comments. Pretty typical blog or discussion board. And they have properties that are pretty simple, nothing too complex. Then we have edges that have particular properties on them as well. I probably could have thought up another one to really drive home that point of an edge that has a lot more interesting properties to it besides type and date. But for this example, that's how it ended up being. So let's get to some actual queries. So let's add a vertex. And again, if you have that, follow that bit.ly link, all the output that we're going to be doing here in Gremlin is there. So I don't want, hopefully people aren't frantically trying to type here and keep up. So just copy and paste from that, paste it in. So we can add a vertex here. Oh, that helps if I load my graph first, doesn't it? So let me go back here and paste that in. G equals tinkergraph. So this will give us a new in-memory, oh, apparently I'm still in some weird syntax mode here. All right, so there's my empty graph. 0 vertices, 0 edges. Let's pop down and go to, we got to let the security system know that we're alive in here. So let's create a vertice. Right, so add vertex. It's a user, Bob at test. Password in plain text. Don't ever do that. But for purposes of this, I think I'm not too concerned about anyone breaking into Bob's account here on my laptop. And we'll add a post from Bob. Okay. So we have Bob. We have a post. Now you'll notice here in the vertex here from this post, there's nothing inside that vertex that indicates, other than perhaps the user display name, but that user display name isn't necessarily in the Bob object, and so there's nothing at this point that links the two, right? That's where we add edges. Okay. So at this point we have Bob. We have him pointed at this post, and so now he's become the author of it. So now if we wanted to search, we could do this. Right? I want to grab all of Bob's posts. That's what that query looks like there, right? G.V, and then I want to find all of them that are of type post. And then I want to go out to the post author, where the post author is Bob, and then I want to go back to that post that I found. Mm-hmm.
You may already mentioned before, but we cannot use wildcard in any of this query.
Use wildcards?
Yeah.
Well, you can do a filter, and inside that filter you can do, I believe inside the Groovy closure, you can put just Groovy code. But it's not going to be leveraging an index when you do that, when you're breaking out into that. If you want to leverage indexes, then you have to do, has to be, I think, part of that has, and not using the closure filter structure. And I think the thing that I sent out is helping you out a little bit more by actually assigning, say for instance, the output of this to a variable named Bob. So definitely use that. I'm not, and it might bite me, but we'll find out. All right, so here's another one. We want to add a timestamp property to the post. Right, so this is a side effect construct where we're just traversing down, and then where we find it, we want to set a property. Right, and there's no necessarily server-side enforced schema, and so we can just add that. And now we can satisfy that query. We want to query, one of the requirements was we want to query by a range. And thanks for reminding me there that at this point it's not exercising any index. And so if you wanted to do this kind of a less than greater than, and that was a key part of your querying, and you need to optimize that, you're going to need to use some of those other indexes. All right, so let's keep going. So now we want to add a comment. So let's add a comment object, or let's add a, actually, we'll add a comment. Ooh. What happened here? Oh, I captured that bracket there. Let's see. I might be trapped inside some weird syntax. All right, let me do this, and I'll catch us right back up.
Question?
Uh-huh.
How do you get the grids?
Those are just, I'm manually entering it. Yeah, it's not being generated. Let's see here, I'll post by range. Okay, so let's just pop this in. All right. So let's grab a post comment. Okay. So here we're going to add a vertex. It's a comment. Oh. Hold on a second. Let's do this. I think Evernote was screwing up my. There we go. All right, so I'll add the post comment again here. All right, so Sally's done a comment for that. Now we need to link it to the post. So just merely adding that comment node doesn't mean that it's connected to that post at all. We need to add that edge. So now we can. This is interesting. We can create Sally now. So I created this comment. The author is Sally. Sally doesn't exist yet, right? And that's totally fine. If someone then wanted to try to query and figure something about Sally, they're going to find a dead end. But it's not stopping me from doing so. It's just a node and an edge.
All right, a question from a few
Yep.
statements back. You had the greater than less than statement.
Yep.
Are those intermediate values materialized? So if that greater than the first statement, it included everything, you end up with the entire graph then going into that second?
Yes, but I believe this has, when you chain hases like that, it's going to be doing that server side. So it's not necessarily bringing the whole graph back to me and then sending it back again for another has.
But it may materialize it anyway on the server.
Yeah, it may. All right, so we can go ahead and create Sally finally, right? And then come back and then link Sally to that comment. Right, so, and I could do these nodes. I could have created Sally, then created her comment, then linked it together, or do it backwards. There's nothing stopping me from doing.
Now, I appreciate this example, but this is not how you create your graph, is it? Or it's not the only way, because I can imagine huge graphs, and you're not going to go one node at a time, are you?
Well, it depends on what your use case is. If you have an existing data set, yeah, you definitely aren't going to. You're going to be loading, you're writing some parser that loads that all up and dumps it in. But if you're starting from scratch, you just release, here's my new message board system, or here's my new blog. As people come in and start signing up and interacting, yeah, your application will be firing these off one at a time to build up nodes, and just like you would if you were to model it in any other database. Just build it up as the interactions occur. But that's a good point. It really depends on what your use case is. If you have an existing data set, yeah, you're not going to be punching this in laboriously one by one. All right, let's query them to get all the comments for the user Sally, and we'll examine this one a little bit. Okay, so here we're starting with all the vertices of type comment. So what you'll notice here is we don't see commands like g.users or g.comments, right? There's no, in this notion, there's no notion of tables or collections inside my graph. It's just one graph. And so a normal thing to do is when you are creating nodes or edges, you always put this type or category or label or whatever you want to call it. So that way, when you're doing these queries, you're saying, okay, starting at all comments, I then want to do this kind of traversal. And then you'll make that an indexed key. And since you're only going to be querying and saying where it equals comment, you're not going to be saying where it's less than comments, right? It doesn't make sense.
You talked about adding attributes or properties to edges, and you have an example of it where you add comment author as an attribute to that.
Yeah, it's on the edge?
Yes. Now, it's obviously a from to.
Yes. This third one, that's a very good question. So this third one here is the actual type. So if we go, let's see here, if I do g.e6, oops, hold on, let me finish this one real quick here. g.e6.map. Sorry. There's that edge that I created. And that third parameter, you'll see there up here we had comment author. That third parameter is special in Titan here, where it will create treat that third parameter as the actual type of the edge, and that's actually a special field for the edges in this database. Yeah.
If you wanted to add additional properties, how would you do that?
Yeah, that's a good question. I think I have an example. Let me peek ahead here. Yeah, here's one right here. Let me expand this a little bit. I'm adding an edge where it's a comment vote, and then it's just a groovy map.
Okay. So
Yeah.
you can keep adding those things with names or tags on them.
Mm-hmm.
So the comment vote is really the type of vote, like the third attribute in that
Yeah.
is
The
the type of,
type of edge. Yep.
and then you can add all kinds of.
You can have add all sorts of properties, and you can add it right up front when you create it, and then also you could add it if you were querying and traversing the graph. You could be adding things as you're traversing.
Thank you.
Yep. All right. So let's see. Where were we? Yeah. Get all the comments from the user Sally. We did that here. All right. So let's do add a vote between a user Sally and a post. So there's Sally voted for Bob's post, and we put a little date timestamp on that. So for denormalization purposes, we may then want to, like a typical use case would be, I want to show the votes, show the posts, but sort them by their number of votes. It could be expensive to try to do that and derive the number of votes each time. So we can go ahead and add a votes property to that post. And so here's this side effect. So I'm doing a traversal, and then once I find the target node, I can do the side effect, which modifies it. Okay. So let's add another post here, getting close to the bottom here. So here's another one, another post Bob created. Let's make him the author. And then now we can do things like, give me the top 5 posts sorted by votes. So let's paste that in and take a look at it. So here we're starting with all the posts. And then I'm going to order them, and then here's where I get a groovy kind of comparison closure, where one in the A and B, IT and A and B are special variables inside this groovy construct, and then you can do this comparison off of the votes. And so if you want to do ascending versus descending, you just switch the A and B. And then here I give an example of, well, I don't want the whole thing. I just want the titles and the votes. Right? I might be displaying it like a table in the UI of some sort. And so I can do this transform where I can select out specific attributes. I'll actually build up this map where the title is equal to the property title, and the votes key is mapped to the votes. And then at the end, I can do this limit. So it looks anyone who's familiar with Groovy, even someone like me who doesn't know too much about it, that's some basic kind of Groovy syntax there. So there we go. So learning Gremlin, 2 votes, and Hello World has 1 vote. All right, so we'll go through here. I don't want to go too much longer and burn into any networking time here. But we can add another vote here. Then we can update the number of votes like we did before. We're just kind of copy and pasting here. And if I'm going a bit fast, don't worry, that link up there has this all laid out. You can literally just copy and paste that file in Gremlin shell, and it will run it all. It's even idempotent. You can keep pasting it over and over again. Add another comment. We're kind of building up towards this use case, this final use case. We've done this before. We're linking the Bob's post to that comment.
Doesn't your shell know to do those comment markers?
Do what?
Doesn't the shell know to do those comment markers?
Yes, and actually I
Whack?
could just do all of it in one whack, and it will ignore these comment markers. Yep. That's how I cheated and caught ourselves up there. All right, so now this is the final use case I'm trying to build up towards here to give you an example of enforcement of certain things. So here we grabbed all the comments, and again we ordered by the number of votes, just like we did with posts. This final one I wanted to talk about a little bit here. What if we had a requirement of we need to enforce no duplicate votes? Right, it's a little bit tricky because I can just create arbitrary edges, and there's I haven't created any kind of unique index to enforce things. So one way to do that is this right here, and I don't know if I need to make it bigger, but where I can build this if statement and say, well, if this post here doesn't have a vote coming from it from this particular user, right, or if it already does have one, then don't allow it to be added. But if it doesn't have one, then go ahead and add it and increment that vote count. Right, it's essentially what that if clause and statement is saying there. So we can see here, if I run this, okay, that one is just an indicator that it went ahead and made that change. And so let's go ahead and grab that output. So there we go. There's that. My first post, number of votes is 2. But if I now run that exact same script, it's just a copy of it here, get a null, indicating that it did not increment, it did not do another vote count, right? And sure enough, let's actually, we can't up arrow because we're using return characters here. There we go, 2 votes, right? It didn't create that extra edge, it didn't increment that counter. Yeah.
Can you set something like a trigger or a validator that will do that automatically?
Yeah, I don't know whether you can. Are you talking about like a server-side trigger?
Yeah.
I don't know. I haven't tried looking into that. That'd be valuable, I think. But I haven't looked into it where, like, if you add a particular edge, that it goes and does some other cascading events or processing. That would be really handy for instance, like denormalization, right? So if you're adding a node and then you wanted to denormalize some of its properties into edges to help with querying, that would be useful. All right, so that's it. I kind of went through the lab a little bit fast, but again, the spirit of it is that if you go to that link or go back to that meetup, all the output right here is there, and you can run the whole thing over again. And I have comments in there, and so hopefully that can be a resource for starting to dive into Gremlin and starting getting your feet wet there. So that's really all I have. There's some additional things to look at. They have MapReduce and so forth, but I wanted to end at least on this slide here. Here's some further resources you can use. There's an interesting one is a sequel to Gremlin, where I pulled some of those examples where they have common things that are done in SQL and what's the analogous way to do it. For me, that was helpful because I, again, come from a kind of a SQL background. It was really helpful to gain some intuition by saying, oh, okay, this kind of query that I've seen a million times looks like this in Gremlin. So, all right, thanks. I went a little bit over, but hopefully you enjoyed it. And are there any general questions? We kind of took as we went, but.
You mentioned that you come from SQL background and you did the graph database. So have you ever did a comparison for similar functionality at the cost resource?
Yeah, I haven't myself. There's, if you go to Neo4j. Oh yeah, thanks. The question was whether there's a comparison between a SQL query and then how that might perform modeled in a graph database. Is that correct? Yeah, so I mean, of course the answer is going to be depends. It depends on how you model it in either end, but Neo4j I've seen in a webcast that they've done where they show if we were to model a friendship network in a relational database, how many degrees of separation could we compute and what does that performance spike look like. And they show that you get very quickly, you get a hockey stick performance in the relational world, but with a graph database, it's much more linear scalability. So it's going to depend. I bet you could probably think of non-traversal type queries where SQL is going to be more performant. But in particular, as you're doing traversals of relationships, graph databases are generally going to outshine a more join-based relational.
How about disk-based footage?
I don't have a lot of insight into that, and it's going to depend, particularly with Titan, what the back end is that you choose, whether it's Titan or Cassandra. Yeah.
So what was the visualization? You spoke about it at the beginning.
Oh, Gephi. Gephi. It's an open source application, and it runs on Java, so it's cross-platform, and you can load up graph files in it. They also have a connector, like a Neo4j connector. They also have streaming connectors. I've written a client for that streaming connector. So if you go to my little website or connection, I think I generally am pretty good about linking, but on my GitHub page, I have a little connectors that I wrote there.
Have you looked at like D3.js for the visualization?
Well, the D3.js? Yeah, so a proof of concept that I can't go into the details of, but what I did for that proof of concept at work was did a graph visualization, and then we wanted to wrap a UI that allowed people to explore that visualization. And so we ended up using D3, and D3 has a graph, I believe, graph visualization.
Force layout.
Yeah, and you can do different layouts, force layout. I don't know if they do the Fructamin or Fructamin, Rheingold, I always mispronounce it, but Gephi that's one thing I really like about Gephi is they have probably a dozen or so different layouts of how you can lay the graph out, which is really interesting. Yeah, I've done just a teeny bit of D3. Yeah. Any other? Yeah.
So one of the things we know that make the relational database model very fast, to get market traction was they settled down very early in SQL for the good or for the bad.
Right.
So they have like a standard API kind of.
Uh-huh.
I didn't see that in the non-SQL world. I think that has been one of the restrictions of the non-SQL times. Isn't the graph technology any ongoing effort to settle down on something that independent of the vendor to choose? Because I think that's one of the key things, when you're going to be going to market. Is anything going on in that?
Yeah, so the question is, let me make sure I restate it correctly, is that so you have all these different graph databases, is there any effort of trying to abstract people away from what's going, all the shifting that's going on, right?
It can be an API, it can be whatever.
Yeah, so one way I mentioned was the blueprints, which it provides a graph abstraction. Another one to look into is Spring Data, which I believe they have graph constructs in there as well. I haven't used it, even though I'm a big Spring fan. I haven't taken a dive into Spring Data for graphs. That's another option.
Interested because what I've seen in non-SQL is that everybody's trying to have their own standard and win on market.
Yeah.
Disaster.
And this, I'll put another.
Are we in the same place here, or as people have understood? Hey,
I think this Tinkerpop stack is a good start at this, right?
Yeah.
It's well componentized into different pairs, and at the lowest layer, you build a mapping to a specific GraphDB implementation.
Yeah, take a look at Tinkerpops. It has, in my opinion, it has a really good potential to insulate you from a lot of that shifting sands. At a higher level, a higher NoSQL level, take a look at Spring Data. Spring Data is essentially trying to do the same thing, but they've also done it for document-based databases like Mongo or CouchDB, and they've also done it for key value type as well.
I can't think of any reason why such a vendor-independent language cannot exist for graphs. Can you?
Graphs are very...
Nodes, edges, properties, there should be a no-brainer.
Yeah, there's not really a reason why there couldn't be one. I don't think the different graph vendors are doing anything so wildly different from the other vendors that you couldn't possibly come up with a layer above that. So I think Tinkerpop is a good way to start. But yeah, I don't think there's any reason why
How do you get management interest in something named Tinkerpop?
Exactly.
That sounds powerful.
Show them Rexter, right? Yeah. So the question was, how do you get management interested in Tinkerpops? I don't know. Maybe you get on Tinkerpop's message board and ask them if they have a more enterprisey sounding name. I will put a plug out for the Thinkerilius folks. I've seen some of the webinars and presentations they've done. Really smart people over there. I only touched on it just slightly, but they have a whole other set of things around graph technologies and a lot of expertise over there. Any other questions? Yeah?
I guess if you're starting out, if you think about starting designing a new application, do you think we should design for this set of interface rather than thinking about the actual database?
Yeah, so
we're not quite there yet.
Yeah, the question is, should we, when we're designing an application, should we design with this in mind? My philosophy, so a little bit of background, so I came from SQL background, and I've had a lot of opportunities at Disney to work in the NoSQL landscape. So I've written applications that go against Cassandra, written Hive jobs, MapReduce jobs, applications where we go against MongoDB, things against. So I've had a lot of great exposure. It's a wonderful opportunity. And one thing I learned real quick is you have to think of your data in terms of its inherent attributes. And there's a tendency to think my data is Mongo, or my data is Oracle, or my data is Titan, right? And the problem with that is you're bound to, if all you think of it is in terms of hammers, you're going to approach everything as something that needs to be pounded into the board, right? So you have to look at all of these as a different tool set, and what you'll see sometimes is an application might have an Elasticsearch component. It might have a Mongo component. It might have a graph component, right? And so as an application's needs start branching more and more out, and you'll see this with a lot of, Amazon doesn't just use Dynamo everywhere, right? They have other backends that they're mixing and matching, but it's all one data set. And so they match the data set, the pieces of the data set that have certain attributes to the database that is well suited to meet those query needs. And I think that's a really good way to go about it. So don't become too zealous towards this. Again, think about that. Do I have a data set where there's nodes, and you can model nodes anywhere, but the real question is the primary thing I'm querying for the interactions? Am I focused on interactions and relationships? And at that point, it starts looking more and more like you should use graph databases. Yeah.
If I have a very large graph and I need to shard it because it's too large to put into memory,
yeah.
What do I look for? Do I just look for like the single connection in my graph and then shard it based on like single connection, because that's the easiest way to cut the graph into two shards? Yeah,
unfortunately, in the proof of concept that I did that used Titan going against Cassandra, we didn't stress sharding. We didn't do a lot of stressing to see how far we could push that. But from what I know about Cassandra, if you use the random partitioner, then it'll do a pretty good job, and that's one of the sweet spots of Cassandra. It'll do a pretty good job of spreading it for you across the cluster and avoiding hotspots on nodes. It's not a surefire thing. You can get in situations where you get hotspotted nodes, but look at Cassandra and some of the things it does with its random partitioner for how it could. Ideally, Cassandra should be handling that for you. You shouldn't have to write a ton of logic to handle that. Yeah. Was there a hand over there, or no? Okay. All right. Well, thank you very much.